Hi, everyone. This is our lesson for Wednesday, the 19th. So at this point, we should have completed section 342 yesterday, which was working on solving quadratic equations using the quadratic formula and finding the discriminant to describe the number and type of solutions to a quadratic equation. Um, our last big topic for this unit is going to be working with systems of equations. So let's first kind of talk about where we're headed, and then we'll talk about what we're doing today as kind of a lead in. So, our big topic that's new as something you've never done before that we're going to be working towards is solving systems of equations where we have quadratic functions involved. Okay. So we could have a quadratic equation and a linear equation. We could have two quadratic equations. Okay. Two quadratic functions where we are working on solving a system with quadratic functions um, in there. So our prior knowledge and what we're going to review today is going to be solving systems of linear equations. Okay, we're going to review both substitution method and elimination method. Kind of my thought process here is um, we or in the past you've learned this going all the way back to eighth grade. So eighth grade you definitely learned how to solve a system of linear equations by substitution method. Then last year you added in elimination method, um, but I thought it would be good to start here because that'll be the basis of knowledge we'll work off of as we work towards doing this with quadratic functions involved. Okay, so um, we're going to take some notes right now on how to solve systems of linear equations using substitution method and elimination method. I'll have a little bit lengthier of an Alex assignment that we can work on where I built in some review as well with what you should have taken earlier in the unit. And then starting tomorrow, we'll start solving systems where we have quadratic functions in there. So kind of old school here. You're what I want you guys to do is get out just a piece of notebook paper, and this honestly should be good practice for us. We don't do this that often in class. I want you guys to work on organization with writing out some notes. So I there's no printed handout for this. The PDF of this is on Classroom for the problems, but I think it's good practice for you guys in organizing notes on a piece of notebook paper. I can honestly say in all the math classes I took in college, it was very rare that I was given any sort of a handout for most of the things. It was just a professor writing a bunch of work up on a dry erase board or up on the boards up front, and we had to just take our own notes. So, good practice here. I want you guys to write down in your notes, if you want to title it Linear Systems Review. I'm going to do, I think I have, how many did I do? Four problems with substitution method and then four problems with elimination method to review these topics from prior math classes. So remember, a system of equations is when we have more than one equation that we're working with. Okay. Um, so when it says solve a system of equations, what you're finding is the ordered pair, okay, the x and the y, that makes both of the equations true. Okay, so you're finding the values for x and y that makes the top equation a true statement and the bottom equation a true statement. Okay, so there's really three cases. We could have no point in common that works in both of the equations. In that case, we say we have no solutions. We could have a singular point, a singular x and y that works for both, and that's the most common case that you'll see most of the time. And then the last option would be if the two equations are actually the same equation written in a different form, then there's many points in common that work as solutions for the two equations, meaning we would have infinitely many solutions. Okay, so you learn two methods using algebra to solve a system of equations. You learn substitution method and you learn elimination method. Reviewing first substitution method, remember the idea of substitution method is if we have an equation in x equals or y equals form that allows us to substitute that number in for x or y. Whole point of that is it gives us an equation with just one variable, which allows us to solve. So I have a variety of different problem types here. The main types of problems you'll see with substitution method. This first one's as simple as it gets. The reason why is if you look at the bottom equation, it's giving us the value of y. It's saying y is -2. In this case, we know already the y value of our solution is -2. Really, all we need to do is find the x value that makes this top equation true for this equation. So what we're going to do is we're going to substitute. We're going to take the fact that y is -2, and put that in for y in the other equation. So let's rewrite that top equation, replacing y with -2. So -2 equals 2x plus 12. And now the result, like I was saying before, is an equation that only has one variable, which allows us to solve for that variable. So we can subtract 12 on, subtract 12 on both sides. -14 equals 2x. Divide by 2. X is -7. Well, we already knew that y was -2. So the solution, the ordered pair that makes both of these equations true, x comma y, would be -7, -2. Okay. Next example, we have two equations that are both in y equals form. So now we need to substitute in what y equals for y in the other equation. So we can take -4x plus 21. Let's put that in for y in that other equation. So let's rewrite the top equation. Y is no longer going to be there. We're going to replace that with -4x plus 21 equals 6x minus 19. And the result is an equation with just one variable, just x. So now let's solve for x. We could add 4x on both sides. So we'd have 21 equals 10x minus 19. Let's add over 19. So now we'd have 40 equals 10x. Divide by 10. X equals 4. So at this point, we know the x value for our solution to the equation is 4. Now we need to find the y. Well, it's going to be the same point for both of the lines. That's the whole point of the solution. So we could pick either of these original equations to substitute 4 in for x. So maybe we pick the top one, going back to the original equations, and let's put 4 in for x. So you have y equals 6 times 4 minus 19. So that'd be 24 minus 19. 24 minus 19 is 5. So the solution, the x comma y pair, that's the solution for this system of equations, 4 comma 5. Okay. So first two examples, both of our original equations were in y equals form. Okay. Now let's look at ones where they're not set up like that. Okay. So if we looked at 3, now only one of them is in y equals form. Okay. So let's take what y equals, in this case -6x plus 10, and let's put that in for y in the other equation. So now we're going to rewrite this top equation, replacing y with -6x plus 10. We have 4x minus 4 times the parentheses. Y goes out, -6x plus 10 goes in. That's 10 equals 16. Notice we needed parentheses because y was getting replaced with these two terms, -6x plus 10. So that -4 has to be multiplied to both terms. Now it's just practice with solving a linear equation. So we need to distribute. We have 4x. -4 times -6x plus 24x. -4 times 10 minus 40 equals 16. We have like terms on the left side we could put together. So we put together 4x and 24x to make 28x minus 40 equals 16. Add over the 40. 28x equals 56. Divide by 28. X equals 2. So we got the x, now we got to find the y. In terms of where to put the x in, if we come back to these original two equations, they both will work in terms of putting in 2 for x and solving for y. We always want to go back to an equation that's already set up in x equals or y equals form for substituting. So the fact that this says y equals on the bottom is going to be much simpler algebra for finding the y. So we can say y equals negative 6 times 2 plus 10. Negative 12 plus 10, negative 2. So x comma y, 2 comma negative 2. That's our solution. Okay, last one. Now we look at this one in terms of trying to substitute. Neither of our equations are in x equals or y equals form, so we have more work to do here. Okay, so if we're going to substitute, the first thing we need to do is get one of our equations into x equals or y equals form. And I should reiterate that it doesn't matter which variable you solve for in terms of x or y, where you can substitute with either. It's not like we had to make everything in y equals. It's just the first three had one or both of the equations in y equals form. So now, if we were trying to get one of these equations to look like x equals or y equals, let's look at the coefficients in front and think about what the simplest way to get nice numbers would be for substituting. Well, if we tried to solve for x or y in that top equation, you would have to divide by a coefficient at some point, which could introduce fractions, decimals in there. We don't want to do that if we don't have to. This bottom equation, since it's just an x here, that's the easiest spot in terms of keeping the numbers as whole numbers that you could get an equation into x equals or y equals form. So let's start by adding 8y over in this bottom equation, because then we would have x equals 8y plus 21. And that guaranteed that we were not going to introduce any fractions or decimals. Now we have this in x equals form, so we can take 8y plus 21 and let's put that in for x in the top other equation. So we're going to rewrite the top equation, replacing x with 8y plus 21. So we have negative 6 times 8y plus 21 plus 3y equals 9. Notice the goal was to just have one variable in our equation, allowing us to solve and get an answer of just a number, and that's what we have here. Let's multiply this out. Negative 48y minus, 6 times 21 would be 126. Then plus 3y equals 9. You can combine negative 48y and 3y to make negative 45y minus 126 equals 9. Add over 126. Negative 45y equals 135. Divide by negative 45. Y equals negative 3. So we got y equals negative 3. Remember, in terms of finding x, the easiest place to go would be something already solved for x. So we already rearranged this equation to make it x equals 8y plus 21. So let's take negative 3 and put that in for y into that equation. So we'd have x equals, instead of 8 times y, 8 times negative 3 plus 21. That'd be negative 24 plus 21. So we get negative 3. So then our solution, x comma y, that would be negative 3 comma negative 3. So that's a review of substitution method. Get one of your equations into x equals or y equals form. Substitute that into your other equation to get one variable. Solve. Then put that number back into either of the original equations, preferably one that's in x equals or y equals form, in order to solve for the other variable, writing your final answer as an ordered pair. So that's substitution method. The other method with algebra that you've used in the past to solve linear systems is elimination method. Remember, elimination method, we align our variables in columns, okay, with x's, y's numbers, or different variables if there's different ones other than x and y. But the key difference here in terms of when to use which method, we want to use elimination, especially when we have big coefficients in front of x and y where they're aligned in columns, because these would be equations that would be difficult to solve for x or y in terms of really messy algebra for substitution. If you looked at one like 5 or even 6, you probably could do this problem with substitution relatively easily, in terms of it's very similar to the one we just did, where you could add the 9x over, substitute in. But here, this is set up perfectly for elimination. Remember, the goal with elimination is to have opposite coefficients, opposite numbers in front of variables, because that allows us to add straight down, eliminating a variable. If we look here, we have a plus 1y and a minus 1y. If we added straight down, those would cancel from the beginning, which is great. Okay, this is set up perfectly to eliminate. So when we add straight down, negative 9x plus 3x, that would be negative 6x. The y's cancel, equals 26 plus negative 8, 18. Well, now we can solve for x, right? The y's are gone. We have one variable left over. So we divide both sides by negative 6. X is negative 3. Okay. Similarly to before, once we get a variable or a number for a variable, we can just substitute that back into either of the original equations or to solve for the other one. We could pick either. So maybe we pick the top one, negative 9 times negative 3 plus y equals 26. Multiply. It's 27 plus y equals 26. Subtract over the 27. Y is negative 1. So then our answer, x comma y, negative 3, negative 1. This problem was perfectly set up for elimination from the start, because if we added straight down from the beginning, the y's canceled. Most of the time, that's not the case. Okay, so if we looked at 6 and we tried to add straight down from the beginning, neither the x's or y's would cancel. Nothing would eliminate. Right? If we added straight down, 3x plus negative 1x would be 2x. Negative 8y plus 2y would be negative 6y. Nothing would cancel. So we can't add straight down yet. Remember, this is where we can multiply an equation by a number that would give us opposite coefficients. And we can do that to one of the equations. We could do it to both. We typically will try to just change one equation if we can. So for example, here, you could eliminate the x's by looking at the coefficients and thinking of a number you could multiply an equation by to get opposite numbers. So if we have a positive 3 up here, and this is a negative 1 here, we could multiply this bottom equation by 3, because that would give us a negative 3x down here, which is the opposite of a positive 3x. You might be thinking about, wait, couldn't we do this for the y's too? You could, and you would get the same answer provided you do all the algebra right in terms of your trying to change the equations, right? You have a negative 8y up here, so you would want a positive 8y down here. How do you multiply, or what do you multiply a 2y by to give you positive 8y? 4. So you could also multiply this bottom equation by 4. Okay, so you have to multiply everything okay, including the number at the end. So 3 times negative x, that's negative 3x. 3 times 2y plus 6y equals 3 times negative 2, negative 6. We're just going to rewrite this top equation above. 3x minus 8y equals 4. Now we have the opposite coefficients where we can add straight down. Add straight down. 3x and negative 3x cancel. Right, these will cancel out. Negative 8y plus 6y, negative 2y equals 4 plus negative 6, negative 2. Sorry about that. Divide by negative 2. So then we get y equals positive 1. Now we can go back to either of the original equations and put in 1 for y. So maybe we pick the top one. 3x minus 8 times 1 equals 4. We have 3x minus 8 equals 4. Add over 8. 3x equals 12. Divide by 3. X equals 4. Answer 4, 1. Okay, try another one. If we looked at 7, if we added straight down from the beginning, the x's would not cancel, the y's would not cancel, so we have to change one of the equations. So this is the process that we'll go through. So if we have a negative 20x here, we want the bottom to be a positive 20x. If you think about how could you change a negative 10x to a positive 20x? Well, we'd have to multiply the bottom by negative 2. Let's multiply everything in the bottom equation by negative 2. So negative 2 times negative 10x, positive 20x. Negative 2 times 5y minus 10y equals negative 2 times negative 5, positive 10. We're going to bring over the top equation. Negative 20x plus 10y equals negative 3. Add straight down. This is a unique case. The x's cancel, right? Negative 20x plus 20x cancel. But also the y's cancel. 10y minus 10y cancels. So really the left side of the equation, we're left with 0 equals negative 3 plus 10, 7. Well, thinking back to all the linear equations we've solved, when the variables cancel like this and we get something like 0 equals 7, well, that's not true. What this is really indicating to us is these two equations would not have an intersection point in terms of if we graphed them. They don't have a point in common. So our answer would be no solution. You might be thinking, when would we get many solutions or infinitely many solutions? If the variables cancel and over here, the numbers canceled as well, and we got 0 equals 0, that would be many solutions. We don't have that here, but that would be when that would come up. So these two equations have no point in common, which can happen with lines, right? If you graph two lines and they're parallel, two parallel lines, they never cross, they have no point in common, and there would be no solution. They have no point in common. Okay, last one for our examples. So we have 2x and 5x, we have negative 6y and 9y. This one's tougher, okay? When we look at our numbers, there's no whole number that we can multiply just one of the equations by that would give us opposite numbers. Okay, whole number, right? You can multiply 2x by a decimal and it would possibly get us to negative 5x. But we don't really want to do that in terms of introducing decimals into all the other spots if we don't have to. So an approach we can take to keep our numbers as whole numbers with multiplying is, let's multiply each of the equations by the opposite coefficient of the variable. So if we have a 2x here and a 5x here, we can multiply the top equation by the 5 from the bottom, 5, and let's multiply the bottom equation by the number on the top, the 2. Only problem right now is this would be a 10x and a 10x, so we need them to be opposites. So let's flip the sign on one of them so we can do the top one as a negative. We could also put the bottom one as the negative. Okay, we'll multiply everything in the top by negative 5. So negative 5 times 2x, negative 10x. Negative 5 times negative 6y plus 30y equals negative 5 times negative 14. That'd be positive 70. Then let's multiply the bottom equation by 2. Okay, so everything gets multiplied by 2, so we'd have positive 10x, 2 times 9y plus 18y, 2 times negative 11, negative 22. Okay, now we can add straight down. We see the x's cancel. 30y plus 18y, 48y, equals 70 plus negative 22, 48. Divide by 48. Y equals 1. Now we can come back to either of the original equations. Let's put in 1 for y. Okay, so we can pick either of the original. Maybe we pick the top one. 2x minus 6 times 1 equals negative 14. So 2x minus 6 equals negative 14. Add over the 6. 2x equals negative 8. Divide by 2. X equals negative 4. So final answer, negative 4 comma 1. So to summarize, today we reviewed substitution and elimination method for solving linear systems of equations. When to use which method? We use substitution when one of our equations is already in x equals or y equals form. We use elimination when our variables are aligned in columns, and it would be difficult to solve for x or y. Specifically, elimination is most useful when we already have opposite coefficients like we had in number 5 here. But it's a pretty efficient method regardless when we just have to multiply equations by numbers and get those opposite coefficients to solve. So it's the two tools you learned in previous classes to solve systems of linear equations with algebra. You also solved systems of linear equations by graphing, where you could graph the two equations and look at where the lines intersect. Where we're headed is we're going to work with quadratic functions. So we'll solve those graphically by graphing quadratic functions and looking at where they intersect. And then we'll also solve it with algebra, and it'll actually stem off of our substitution method. Okay? But that's our lesson for today. Our homework for tonight is in the ALEKS program. I did build in some review with topics from prior days, including what we did yesterday in there. Okay, but we have a little bit lengthier of an ALEKS assignment in there. So you will see, I believe it was called Systems of Linear Equations Homework. So we come back over here to our calendar. Solving Systems ALEKS assignment is our homework. Okay, nice thing there is I can check that in from here and give you guys credit for that. Reminder, your homework for today was the 342 bookwork. Make sure you have that done for when I return so that I can check that in and give you credit for that. If you had questions on that, check the answers in the back of the textbook. If there's anything that's not making sense or you want me to explain, feel free to shoot me an email, and I'm happy to work something out or do whatever and try to clear up any issues. So, new lesson tomorrow, but hopefully this one made sense with substitution elimination, a topic that you've seen in previous years. And then, again, any time remaining here in our homework for tonight is to work on this ALEKS assignment. Hope you guys have a good rest of your day, and I hope to see you all soon.